I press that, don't I? That won't stop it. So we're going to continue on with graphs of inverse functions. So we're in the process of doing this question, drawing the line of reflection y equals x, which I've done here in yellow. And use it to sketch the inverse of the function below. So this is normally a parabola. Is a quadratic normally 1-to-1? A quadratic graph, would it normally be a 1-to-1 function? No.
No.
How has this suddenly become a 1-to-1 function?
Because we've excluded the two. No, it's like x has to be greater than 3/2.
Yeah, that's right. Exactly, yeah. But yet we've restricted the domain of this quadratic so that it's kind of only x is greater than 2. So now it's a 1-to-1 function, because a 1-to-1 function, a horizontal line could only cut once. So it's a 1-to-1 function. If it's a 1-to-1 function, what does it mean about its inverse?
Doesn't exist.
It does exist, yeah.
It does
Yeah,
exist.
it does exist. If it wasn't 1-to-1, like if it was a regular looking quadratic, what does that tell us about its inverse function?
Yeah, maybe highlight that.
So I'm probably not being clear. So see, if it looks like this, does the function exist for this graph here? Does the inverse exist for this one? No, it doesn't, because it's not 1-to-1. This graph here, it is 1-to-1. Does its inverse function exist?
Yes.
Yeah, it does.
Wait,
Yeah.
so inverse functions can't exist if it's not 1-to-1.
Yeah, exactly.
Why?
And you should do
That's a very, 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 very good question. I'll explain that another day. So we'll do another day.
That doesn't make sense.
So we'll do, yeah, it seems a bit weird. So another, because it's kind of like maybe something I can pop in as an extra TOK thing. Like, why does an inverse function not exist for non-1-to-1 functions? So that's a very good question that I can pop in an extra TOK thing. Shh. Okay, guys, please pay attention. Thank you. Okay, so we've got this graph here, and we were asked to sketch its inverse. So remember, once you draw the line y equals x, if the original function cuts that line, y equals x, then the inverse function is going to cut it too. So that's why I plotted points. I plotted a point here. And plus also see the x-intercept here. So the y-intercept of the inverse is going to be here. This one's at 3-to-1. So this one will be at 1-3. And then and so on. So you can kind of like then, and then this one's kind of gone across this way. So this one will have gone down this way. And so now we can kind of draw it. I'm going to try to draw it freehand, which is always a risk on this keyboard. So see, it's got a cut through that point as well. And there we go. There's our dodgy looking inverse function. Yep, so that's the inverse function. Something interesting we might observe here as well. Do you have any questions about how I sketch that? Do you notice that each point is kind of equidistant, like this red point should be equal distance from the yellow line as that point? See, that one's equidistant. They're like, so y equals x should be a line of symmetry, or like a axis of reflection. So it's meant to be a line of symmetry as much as possible. So see, if that x-intercept is 2, then the inverse is y-intercept should be 2. And that one flips over that way. So yeah, they're reflections of each other. Something interesting you might notice too about the domain and range if you have an inverse function and the original function. You compare them. Say the domain and range of the original, which is in red, and the inverse function, which I did in blue, and describe what you observe. So the domain of this one was kind of like already mentioned. What is the domain of the red one? It's kind of mentioned on the equation above. Yeah, x is greater than or equal to 2. What about its range of that one? Yeah, y is greater than or equal to 0. There's no dot up the top.
For which one?
For the red one, yeah. So I'm sort of allocating the original one.
X is greater than or equal to 2, and the range is y is greater than or equal to 0.
You're talking about for the original?
Yeah.
Yeah, for the original, yeah, you're right. Exactly. So x is greater than or equal to 2, because see, it's going on infinitely from 2. It's going on infinitely wide. And the y value it starts at, the original one starts at, is at 0, and then it goes upwards infinitely. There's nothing at the top of that red graph telling you that it finishes. There's no dots or anything. So the inverse function, I'll do in blue. What is the domain of the inverse function?
X is greater than
equal to 0.
Greater than equal to 0, because it's including that point. And what about its range?
X is greater than equal to 2.
Yep.
I mean Y.
Oh yeah, thank you. That's probably right. So y is blue. So I've done the original, that's why I'm colour coding. So I did the original one here, the inverse one here. Y is greater than equal to 2. As Krista noted, coming up just like that. And so describe what you observe about them, the two. What could you say, conclude about the relationship between you? Yeah, they're kind of reflected, yeah, or opposites, yeah. So it's like the domain kind of of the original matches the range of the inverse.
yeah.
So you could write that in your own words if you want, like don't feel like there's a right way to write it, whatever makes sense to you. Like the domain of the original one is like the range of the inverse, and the range of the original is like the domain of the inverse. So, or how you write it however it makes sense to you, for example. So the domain of the original is similar to the range of the inverse the So I'm running out of space a bit, so I'll just say and vice versa. So I don't have much space to sort of continue on, so I'll just write it like that and just say and vice versa. So as you notice, the domain kind of matches a bit more with the range of the inverse, and then that one becomes more like that one. So they sort of reflect, or you write it, as I said, in your own words, whatever it takes for you to sort of like look back and remember and understand what was written. So if how I read it doesn't make sense, you write it your way. That's pretty messy. And that's meant to be the case for the functions and their inverses. So if there was a question and they didn't even give you the function, but they said its domain and range was this and this, and they asked you to say, state the domain and range of the inverse. So that could be possible. They could ask you. They could just give you the domain and range and not even tell you the function, and ask you, therefore, to say what would be the domain and range of its inverse. That's possible. Yeah, yeah, exactly, for any function. So long as its inverse exists, of course. So if its inverse exists, in this case of range, the domain had to be restricted. So therefore the range and domain of the inverse was also restricted. So that is possible that they could ask you that to prove that you've got knowledge that for one it has to be one-to-one for the inverse to exist, and also that they're kind of like opposites of each other. The domain becomes like the range of the inverse. And so on. Da-da-da. Pretty weird. Okay, here we go. So the next page, almost through graphs of inverse functions. So the fact that a one-to-one function and its inverse are reflections across the line y equals x, yep, keep putting that in there. So the fact that they're reflections across the line, like kind of mirror images across the line y equals x, offers us a way of testing algebraically if two functions are inverses of each other or not. So imagine you weren't dealing with graphs at all, but just purely the algebra. So a classic question could be, just verify that that thing and that thing are actually inverses of each other. The way you can test it is if you combine them both to make a composite function. If you can, then the composite function, so like because it's reflections in the line y equals x, the composite function, when you simplify it, should simplify down to x. So we're going to practice composite functions of these two. So the question could be, verify that these two are inverses of each other. But they want you to do it algebraically and not graphically. So one way is you could have done it graphically. You could have graphed them and proven that they're reflections across the line y equals x. But imagine this one, I want you to do it algebraically. So you would have to find the composite of these two and then prove that it simplifies down to x. And because there's two different ways we can do it. Can anyone see why there's two different answers? Like we'll split a line down the middle and we'll do it two different ways. Yep, Paige? Yeah, exactly. You could have it first of all where the mother function is f of x, then you could do it also when the mother function was g of x. So we'll sort of split it. I'd say because that's why I gave you a whole page for this one. We'll split it down the middle, and we'll try both just to practice our algebra. Because they're kind of awkward because you've got kind of fractions going on here. So let's split it down the middle.
I'm going to split in the middle.
Oh, I didn't expect it to do that. And it didn't
Miss
even
Mary, you said to split it in the middle.
split down the middle. So we'll split our little page down the middle. And on one side, I want you to on one side I want you to find f of g of x. And on the other side, I want you to find g of f of x. Just to practice our algebra, it's good practice for finding composite functions. And I'm going to give you, and a little clue is, once you've simplified it all down, it should simplify down to x. If you were to verify that they're inverses. If it didn't simplify to x, then they're not inverses. But it is kind of stating to you to verify that they're inverses, so maybe it's a clue that they might be.
For f of g of x, do you put the gx in both of the x's and the f of x?
Yeah.
Okay.
So it's pretty messed up.
Yeah.
That's why I've given you a whole page for it. So it's up to you. You might want to split it. If you want to split it down horizontally, you can do that if you want, but it takes a fair bit of space, this. So I'll just pause this for now. Okay, here we go. So Chris is going to talk us through how we initiate the whole thing.
Okay,
So listen up, please. Thanks. Shh.
the formula for f at g at x is 3x plus, or should I just go straight into it since you're reading it? Okay.
Just the whole thing where you subbed it in, I'd say.
Yeah,
The whole subbing, the big awkward subbing in bit. That's why I've given you a bit of extra space.
Okay, so then I sub in x subtract 3 of this. Over. Okay.
Do you have questions about that?
So I just put it, this is also like, kind of, like 3 over 1. When I did that, it kind of made it a bit more understanding. Then I just multiplied the top. So 15 over x subtract 3 plus 5 over 1 divided by 5 x subtract 3. So then, in order to add it, we have to have the same denominator. So then I multiplied it by x subtract 3, and whatever you do to the top has to do the bottom, and vice versa. So then that becomes 15 over x subtract 3 plus 5x subtract 15 over x subtract 3.
All over? Yeah, and then we'll ask a question. Yeah.
And then all over x sub that.
So it sounds like you might have some questions about what happened there. Sorry.
Okay, so then you just put this is basically on the same thing. So 15 plus negative 15 just cancels out to 0. So then on the top, you just end up having 5x over x subtract 3. Basically over, I did it this way because I like it better this way, over 5 over x subtract 3. And then you just have to multiply by each other.
Oh, if you want, I'll scroll down. Sorry to mess you around. Just so it's all flowing. I'll give you some more space too. There you go.
Okay, so then you just flip it and multiply it. So 5x over x subtract 3 multiplied by x subtract 3 over 5. And then this becomes 5x squared, which you multiply this and that. So 5x squared subtract 15 over 5x subtract 15.
Yeah, good.
And then this cancels out.
Yeah, or you could maybe factorize it first. Factorize the top and bottom first. Might be
Okay.
good.
So then 5x squared subtract 3. And this becomes 5x subtract 3.
Oh, yeah.
Yeah.
You can do it that way. Yeah.
So what did you mean?
I actually meant like you can cancel those and those. But actually, yeah, keep doing this one because that one can be factorized out quadratically.
It's not 5x times negative 3, it's just 5 times negative
5 times 5x and then subtract 15.
Then you mean this bit?
Yeah.
What about that bit? 5x over that. And see how she did keep change flip? Krista did.
3. Oh, yeah.
So you can have
Negative 3 times 5x is 15x, like negative 15x.
Oh, that's it. Okay, that's probably what's messing us up. Yep. Okay, got it. Yep. Thank you. Yep. You're right.
So
Okay, that's going to fix us up a bit. Actually, that's good. Yeah, because that means there's going to be less work. So yeah, correct. Good. Because now this is going to make it work out.
Yeah.
Good. Yeah.
so now you said factor it out. So it's
Yes.
back to 5x.
Yeah. Back to the step you were just doing before.
5x x subtract 3.
Yep.
Over 5x subtract 3.
Okay. What?
And then this cancels out.
Yep.
And then 5 cancels out, and then you just end up with x. Right there.
Well done. Isn't that amazing? That big, horrible, complicated thing just simplified down to x. So what have you just confirmed about those two functions? They're inverses of each other, supposedly, algebraically anyway. And another thing that, at this point, like what I was, I'm pretty lazy. So remember fractions, if you're multiplying fractions, you can cancel down diagonally when you're multiplying fractions. So you could have cancelled down that, and 5 and 5 at that point too. So no problem with doing it this way. So when you're multiplying fractions, you can cancel down x minus 3x minus 3. We're talking about that set there. And 5x and 5 cancels down. So that cancels. And that cancels. Also, so at that point you could have cancelled it down and got an x if you need to. Because you left with that little x there. Do you have questions about that?
Yeah, that's what Mike said. You can cut it down like that.
Yeah, at that point, yeah, when you're multiplying fractions, it's kind of a bit like saying 2 over 5 times 4. 2 over 5 times 10 over 3. So when you're multiplying fractions, remember before you multiply, you could also cancel diagonally. So 2 and 3, does that cancel down diagonally?
No.
Yeah. 10 and 5?
Yeah, 2.
Yeah, so you could have cancelled that to like 2 and 1. So that's the kind of style of step I've done there. And then I would have done, and then x just times nothing because they're both cancelled down. X times 1 basically. So that would have been 4 over 3 for that one. So back to cancelling down stuff. That is awesome. So what I'll do is I'll just pause it at this point. Here we go. So we're about now trying.
Oh, Miss Maloney, that one's easier.
Yes.
Yeah, much easier.
Oh yeah. Can you just show a middle step between here and here? Like kind of like what I mean is like just something like that.
Yeah.
You actually do.
Oh, you're sad.
Okay, yeah, the next one. Now we've done the first one too. Yeah, there's less work. It's less messy than the first one, but the same kind of idea. So we're finding. What are we finding? G of f of x. Do you need a bit more space too? Do you want to like do it a bit off to the side? So the little undo button's kind of helpful too, or you can erase. Oh, There you go. Okay, yeah, so maybe just move over to the side. Okay, watch with interest, Bella, please. Thank you. G of f of x. So the mother function this time is g of x. Yep, so always good to write the original substitution step. So then you at least get a method mark. It's an easy method mark to get. Oh, why did Bella do this? You don't need to write. You're doing it right.
But she also to be able to subtract, she needs the same denominator.
Yeah, same denominator. Yep. What do you think Bella's going to do next?
She's gonna try for this.
Yeah, why did it become 5 over x on the bottom? Oh, we can ask. You can picture it. Oh, yeah, someone else.
Do that.
What?
Because it cancels.
Yeah, the 3x cancels out, doesn't it? 3x plus 5 minus 3x, yeah. You combine like terms. Yay! Good. Yeah, so that little dot in this case is meaning a multiply sign, of course.
Yeah, I like to use dots as well.
It is handy when you've got x's everywhere.
Yeah.
Like if you've got x's all over the joint, the little dots could be handy.
Yeah, I mean, I don't like
They do, yeah. I did two giant loopy brackets next to each other, but then it can get a bit brackety. Any questions about that? Pretty brilliant. Love your work. Is that the end of inverse functions? It is, yep. So our next lesson is reciprocal modelling. So I'll just stop the video there so we can